In today's video, we're going to use our understanding of point charges in Coulomb's law to solve for the electric field due to a line charge with a uniform charge density of 5 lambda coulombs per meter. So, we have ourselves a line charge with an axis z with a constant lambda 5. So what does this tell us? Well, it tells us that there's positive charges on the plus side of the z-axis, and there's plus charges on the negative side of the z-axis. We can see from the symmetry that the net electric field will be pointing to the right in the x direction. We can identify this due to the symmetry of the charge distributions along this infinite line. Alright, so now we want to be able to integrate a part of this line, so we can take a typical element or an infinitesimal element, point charge. We can call this dz, and we can draw this out to where we want to find the electric field. Alright, so now our infinitesimal element to this point out here, we can label as r, and we can label this axis as z. And Coulomb's law would dictate that our point charge is equal to k dq over r squared. So our point charge, dq, will create an electric field with, when multiplied by k and divided by r squared. So what does this mean to us? Well, our dq can be turned into lambda dz, and when we do that, we're just saying that the charge density is multiplied by our point charge. Alright, so we can write dE as k lambda dz over r squared. Okay, and now, since we know our E field will be pointing in the x direction, because we do not have any y components here, we can just worry about our electric field dE x. So our x component of our electric field, which would be dE cosine theta. Cosine for our function would be x over r. So this becomes x over r. So our dEx will be equal to k lambda x dz over r cubed. So all we did here is we replaced our cosine with what we have written out. So as long as we have a good picture, it's really easy to set up this problem. Alright, so the next step is to integrate. So to integrate, we can isolate a few things. We can move k, and we can move lambda, and we can also move the x to the front. So now we just have the integral dz over r cubed. Alright, so this will be our E field at the end. In order to solve this problem, we will be using trig sub. You can also alternatively use U sub. So which one should you usually choose? Well, it's dependent on your numerator value. Say we have an integral, such as this, dx over x squared plus a squared. This would be a great candidate for trig sub. Say we don't have an even function on the top. Perhaps we have an odd function. We'll have an integral like x cubed dx over x squared plus a squared. This would be used with U sub. Both have their uses, and one is easier than the other depending on your numerator value. So how do we use this to solve our problem? Well, by using trig sub, we can define our triangle, which we have done earlier here, where we have r, z, and x, our theta. we can use trig sub to identify different parts of our triangle. So, for instance, tan theta here would equal z over x. Sine theta would equal z over r. And then cosine theta would equal x over r. So we can use this to solve for our problem because doing the integrals of tan, sine, and cosine is relatively easy. Another thing to add is theta here is the integration variable. So when we do our integration, we will be integrating with respect to theta. Theta for our problem would be going from pi over 2 to negative pi over 2. Okay? So we have dz over r cubed. So how do we solve for this? Well, by using trig sub, we can say that z over r is equal to sine theta. We can say that x over r is equal to cosine theta. And we can say that z over x is equal to tan theta. So we want to be able to find the value for dz and r. So our values will be z is equal to x times tangent theta. Our dz, our derivative of z, will be x secant squared theta d theta. And our r will be x secant theta. So we're just using basic trig to solve for all of these. So we have our z, our dz, and our r. And we can plug that into our equation. All right, so let me just clear up some space here. Up at the top. Oop. Just clear some space. And what we'll get of x secant squared theta d theta over x secant theta cubed. All right. So if we were to cancel out a few things, we can cancel out an x on the bottom. And that will give us a value of 1 over x squared, which we can move to the front. And the derivative, or the integral, cosine theta d theta. And then if we continue on with this integral, we'll get 1 over x squared sine theta. And we want to be able to understand what part of this we're integrating. So since we have a straight line in the positive z and the negative z, we can say that we're looking at this from negative pi over 2 to pi over 2. This will equal this whole portion, the sine, this whole integral will equal 2. And then when we multiply that by 1 over x squared, we get 2 over x squared. Okay, so now we can take this whole thing and we can drag it to our E field equation that we have written from earlier. Let me just clear some more space here. What we end up getting at the end is we can get E field is equal to k lambda x times 2 over x squared x hat, because we are going in the x direction. And we can equal that to lambda over 2 pi epsilon naught x hat. So where did my k go? Well, the value of k is equal to 1 over 4 pi epsilon naught. So we just plug that into our k, and that is how we are getting lambda over 2 pi epsilon x hat. And now our last part is to replace the value of lambda. So the value of our lambda, or our charge density, is 5. So then we just replace the lambda in our answer. So we have 5 over 2 pi epsilon naught x hat. And that is our final answer for the electric field of this infinite line charge.